Hot water freezes first? You bet. Hey there, science fans. Have you ever heard someone say, hot water freezes faster than cold water? You probably thought they were pulling your leg, right? It sounds crazy, but it can actually happen. It's called the Mpemba effect, and it's a real head-scratcher. Get ready to dive into the wacky world of water and learn why sometimes hot beats cold in the race to become ice.
We all know that water freezes at 0 degrees Celsius or 32 degrees Fahrenheit. So how can hot water, which has farther to cool down, possibly freeze faster? It's a question that has puzzled people for centuries. Let's investigate.
Our story begins in the 1960s with a Tanzanian student named Erasto Mpemba. Erasto was a bright and inquisitive young man, always eager to learn and explore the world around him. He attended a local school where he was known for his curiosity and determination. One day, during a school activity, Erasto was making ice cream in the school kitchen. As he carefully mixed the ingredients, he noticed something peculiar. His mixture, which was still warm, seemed to be freezing faster than the mixtures of his classmates, which were already cold. This observation puzzled him. Erasto couldn't believe his eyes. How could a warm mixture freeze faster than a cold one? He decided to conduct a small experiment right there in the school kitchen. He prepared 2 batches of ice cream mixture, one warm and one cold, and placed them in the freezer side by side. To his amazement, the warm mixture froze faster once again. Imagine that.
Intrigued by his findings, Erasto couldn't wait to share his discovery with his teachers. He approached them with excitement, explaining what he had observed. He asked them why the warm mixture froze faster than the cold one, hoping for an explanation. To his surprise and disappointment, his teachers were skeptical. They dismissed his observations, insisting that it was impossible for warm water to freeze faster than cold water. They believed it was a mistake or a fluke, and they didn't take his discovery seriously. But Erasto was not one to give up easily. He was determined to prove that his observations were correct. He continued to experiment on his own, meticulously documenting his results. He repeated the experiment multiple times, each time observing the same phenomenon. His determination and persistence were unwavering. Eventually, Erasto's efforts caught the attention of a visiting physicist named Dr. Dennis Osborne. Dr. Osborne was intrigued by Erasto's findings and decided to investigate further. He visited the school and met with Erasto, who eagerly shared his observations and experimental results. Together, Erasto and Dr. Osborne conducted a series of experiments to explore this curious phenomenon. They carefully controlled the conditions and meticulously recorded their observations. Their collaborative efforts paid off, as they were able to consistently reproduce the results that Erasto had initially observed.
What they discovered was remarkable. Under certain conditions, hot water did indeed freeze faster than cold water. This counterintuitive phenomenon challenged the conventional understanding of thermodynamics and sparked curiosity among scientists worldwide. The phenomenon was named the Mpemba effect, in honor of the young student who had the courage to question the status quo and pursue the truth despite skepticism. The Mpemba effect remains a topic of scientific investigation and debate to this day, with researchers exploring the underlying mechanisms that cause this surprising behavior. Erasto Mpemba's story is a testament to the power of curiosity, determination, and the willingness to challenge established beliefs. His discovery not only contributed to the field of science, but also inspired countless others to pursue their own questions and never give up in the face of doubt. The legacy of the Mpemba effect continues to remind us that sometimes the most unexpected observations can lead to groundbreaking discoveries.
Now before you go dumping hot water in your ice cube trays expecting instant ice, there's something you should know. The Mpemba effect isn't something that happens every single time. It's a bit more complicated than that.
You see, the way water freezes depends on a bunch of different things. Things like the starting temperatures of the water, the type of container you're using, and even the surrounding air temperature can all play a role. Sometimes the hot water wins, and sometimes the cold water does.
Think of it like a race. Even if one runner gets a head start, the other runner might still win if they're faster or the course conditions favor them. It's the same with freezing water. There are many factors that can influence the outcome.
So, why does the Mpemba effect happen at all? This phenomenon, where hot water freezes faster than cold water, has puzzled scientists for decades. It's counterintuitive, isn't it? You'd naturally think that colder water would freeze first, but that's not always the case.
Well, scientists have a few ideas, and it likely comes down to a combination of factors. It's not just one single reason, but rather a complex interplay of various physical processes. Let's dive into some of the leading theories that might explain this curious effect.
One explanation has to do with evaporation. When you heat water, some of it turns into vapor and escapes into the air. This process is more pronounced in hot water compared to cold water. As the water evaporates, the overall volume of water decreases. This means there's less water left to freeze, and less water freezes faster. It's like having a smaller ice cube tray. It takes less time to freeze a smaller amount of water. This reduction in volume due to evaporation is a significant factor, but it's not the only one. There are other processes at play that contribute to the Mpemba effect.
Another idea involves something called convection. Convection is the movement of fluid caused by differences in temperature and density within the fluid. Hot water is less dense than cold water, and this difference in density creates currents within the water as it cools. These currents, called convection currents, help to distribute heat more efficiently throughout the water. These convection currents can lead to faster cooling because they move the warmer water to the surface where it can lose heat more quickly. This efficient heat distribution might be another reason why hot water can freeze faster than cold water.
And what about those tiny bubbles? Water often contains dissolved gases, like oxygen and nitrogen. These gases are more soluble in cold water than in hot water. When you heat water, these gases are released and form bubbles. These bubbles rise to the surface and escape into the air. The presence of bubbles can interfere with the freezing process. Bubbles can act as insulators, trapping heat within the water and slowing down the freezing process. These bubbles might interfere with the freezing process, potentially slowing it down. Since hot water loses more dissolved gases, it might freeze faster than water that still has lots of bubbles. So, in summary, the Mpemba effect is likely due to a combination of evaporation, convection, and the behavior of dissolved gases. Each of these factors plays a role in how water cools and freezes. While the exact mechanisms are still being studied, these theories provide a fascinating glimpse into the complex world of thermodynamics and fluid dynamics. Scientists continue to explore this phenomenon, conducting experiments and developing new models to better understand it. The Mpemba effect reminds us that even everyday occurrences like freezing water can hold surprising mysteries waiting to be uncovered. As we delve deeper into the science behind the Mpemba effect, we not only learn more about the behavior of water, but also gain insights into the fundamental principles that govern our physical world. It's a testament to the endless curiosity and ingenuity of the scientific community. So next time you see water freezing, remember that there's more going on than meets the eye. The Mpemba effect is a perfect example of how science can turn the ordinary into the extraordinary, revealing the hidden complexities of nature.
Hold on to your hats, science fans, because things are about to get even more interesting. Today, we're diving into a fascinating phenomenon that has puzzled scientists for decades. It's a twist in the tale of how water behaves when it freezes, and it might just blow your mind.
There's another phenomenon that might be involved in the Mpemba effect called supercooling. This is where things get really intriguing. Supercooling isn't just a cool term, it's a process that defies our everyday expectations of how water should behave. Supercooling is when a liquid, like water, is cooled below its freezing point without actually turning into a solid. Imagine having a glass of water that's colder than ice, yet still liquid. It's like the water is playing a trick on us, staying liquid even when it's cold enough to freeze. It's like tricking the water into staying liquid even though it's cold enough to freeze. This happens because the water molecules need a little something extra to start forming ice crystals. It's not just about the temperature, it's about the conditions that allow freezing to begin.
Supercooling can happen because the water molecules need a little something called a nucleation site to start forming ice crystals. These nucleation sites are like the starting points for ice to form. Without them, the water can stay liquid even when it's below freezing. These nucleation sites can be impurities in the water or even just tiny imperfections in the container. Think of them as tiny seeds that help the ice crystals grow. Without these seeds, the water remains in a supercooled state, waiting for the right moment to freeze. If there aren't enough nucleation sites, the water can remain in a supercooled state until something triggers the freezing process. This trigger could be a sudden movement, a tiny impurity, or even a change in temperature. When it happens, the water can freeze almost instantly, creating a dramatic and fascinating transformation.
Some scientists believe that hot water might be less likely to supercool than cold water. This idea adds another layer of complexity to the Mpemba effect. The heating process might play a crucial role in how water freezes. This could be because the heating process removes some of those pesky impurities that act as nucleation sites. When water is heated, it can drive off gases and other impurities that might otherwise help ice crystals form. This means that hot water could have fewer nucleation sites compared to cold water. Without those impurities, the hot water might start freezing at a higher temperature than the supercooled cold water, giving it a head start in the race to becoming ice. This head start could be the key to understanding why hot water sometimes freezes faster than cold water. It's a race against time and temperature, with the hot water potentially having the upper hand due to its purity. Researchers are continually exploring these phenomena, setting up meticulous experiments to observe and measure the effects. They use precise instruments to monitor temperature changes and the behavior of water as it cools and freezes. Every detail matters in this quest to unravel the mysteries of supercooling and the Mpemba effect. At the molecular level, water is a fascinating substance. Its molecules interact in complex ways, influenced by temperature, pressure, and impurities. Understanding these interactions is key to explaining why water sometimes behaves in unexpected ways, like supercooling or the Mpemba effect. The data collected from these experiments is analyzed carefully, with scientists looking for patterns and correlations. They use advanced software to model the behavior of water and predict outcomes under different conditions. This research not only helps explain the Mpemba effect, but also contributes to our broader understanding of thermodynamics and phase transitions. As scientists continue to investigate, each discovery brings us closer to fully understanding these intriguing phenomena. The Mpemba effect and supercooling are just two examples of how water can surprise us, challenging our assumptions and sparking curiosity. The journey of discovery is ongoing, and who knows what other chilly twists await us in the world of science.